My name's Alex Pegan, along with Jesse Kreisfeld and Matt Stoll. Our senior design project is a behind-the-meter solar garden load following with zero injection control. Our industry sponsor is Missouri River Energy Services, and our faculty advisor is Dr. Zinkowski. I'll be talking about the project background and motivation. Matt Stoll will be talking about the hardware implementation, and Jesse Kreisfeld will be talking about the economic analysis we have done. As I said, Missouri River Energy Services is the industry sponsor for this project. Missouri River is an organization of 61 member municipalities that own and operate their own electric distribution systems. They supply their members with reliable, cost-effective, long-term energy and energy services. Clean energy is a high priority for Missouri River and their members. They will be continually adding renewable, carbon-free resources to their power supply mix. Missouri River is looking to add a solar garden behind the distribution meter at one of their member communities. There are a few reasons why it would be placed on the distribution side. One, it is cheaper, and two, it can be implemented much faster than if it were integrated on the transmission side. The primary concern when doing this is that it cannot inject power back on the transmission grid due to regulations. Therefore, the output of the solar garden cannot exceed the load on the distribution system. If this were ever to happen, the output must be curtailed. This project is to design a control scheme for a behind-the-meter solar garden in order to operate according to industry regulations. This control scheme will read the load on the distribution system and compare it to the output of the solar garden. When the output approaches the load value, it will control the inverter to curtail its output. An economic analysis was conducted to determine the most optimal sizing of the solar garden for a particular member. All right, I'll be leaving it for Matt now.
Thanks, Alex. So now I'll talk a little bit about the hardware portion of our project, and we'll get started here looking at the one-line diagram. So over here on the right-hand side is the transmission interconnection point, where the transmission level voltage gets stepped down to the distribution level through a transformer, and then goes on to feed the distribution load directly. So that's basically the existing system, along with an SEL power meter to keep track of how much power is being brought in throughout the day, so that the municipality can purchase energy accordingly from the transmission utility. And there'd also be existing communication between that power meter and an SEL real-time automation controller, which then relays information back to the supervisory control and data acquisition system of the municipality. And then what we'd be adding is down here in the dash box, which is a solar garden, which consists of a PV array, which generates DC power and then gets converted to AC through an inverter, and then injected directly onto the distribution grid located here. And it'd also be a very similar SEL power meter to what's already existing at this location, to keep track of how much power is being injected from the solar garden, and then sending that information over to the real-time automation controller to be used for the municipality's own reporting purposes. And then we ensure that power is not over-injected by keeping track of how much power is being demanded by the distribution load at all times through this Fronia smart meter, and then sending that information to our inverter as the maximum power set point, so that we're not injecting more power than the load is demanding.
All right, so here's our setup in the microgrid lab here. This is our three-phase inverter that we've been using, where we have our DC inputs, which are from the PV array located on the rooftop, which we tie in through the wall there. And then we have our three-phase AC output, which goes on to feed our distribution load, which is our variable load bank down here. And then it ties into the utility grid through that wall. And then we'll watch what happens when right now we have no output from our inverter because we have no load. And when we turn on our load, we'll be able to see, here's our load power here, about 3.6-ish kilowatts. And then our solar garden output, you can see it ramping up, and it'll end up matching the output pretty closely. And this bottom number down here is how much power is being brought in from the transmission grid. So basically, the sum of the bottom two numbers equals the top. And you can see that it'll approach the load power. Keeps getting closer and closer. So within about 10 watts or so, and then we can see when we turn the load off, it'll go down. So our load went to 0, and you can see our solar garden output went to 0 as well. So we're not injecting power backwards onto the grid. All right, I'll hand it over to Jesse.
Thanks, Matt. So in our project, we also did an economic analysis, and we created a tool to help determine the optimal sizing of a solar garden in this location. So up here, you can see a bunch of input variables, such as rates. If they may change over time, it can update in this tool. And then down below here is all our data and calculations used to help determine all our outputs. And up here is all of our outputs. So some key ones to make note of is like install cost and yearly on operation maintenance cost. And then here we have our net flow savings. So that's the money that we'll save by generating the solar and from different demand and capacity charges, for instance, subtracted by that yearly maintenance cost. And that will give you your yearly intake projected. And of course, this isn't an end-all analysis. There are many other factors that can go into this. And then here we have some graphs. So here is that yearly net dollar amount, and it's for the two different substations being looked at. And you can see it doesn't start to deviate from each other until around that 7 megawatt range. And then down below here, we looked at an undersized of 3, right-sized for this area for the load at 5, and an oversized of 7. And you can see how much money we lose as an oversized installation due to the curtailment that would happen. So looking at that 5 megawatt, we barely lose any. So that looks to be about the right set point. Thank you.